Hi, my name is Paul Newman. I'm Chief Scientist for Earth Sciences at the NASA Goddard Space Flight Center. Today I'm going to give you a presentation on the Antarctic ozone hole. I'm going to give you some of the history behind the discovery, the causes of the ozone hole, what's going on right now, and what do we expect into the future. So the ozone hole was discovered in 1985 by these three gentlemen. On the left, Joe Farman. In the middle, Brian Gardner, and on the right, John Shanklin. And the star of the show is a Dobson spectrophotometer that they're standing around. Now, the Dobson spectrophotometer measures the total amount of ozone above our head, so the total column amount. We measure that with units of Dobson units. 300 Dobson units represents a layer 3 millimeters thick. If you could bring all the ozone down to the surface, it would form a layer 3 millimeters thick. That is equivalent to 2 pennies stacked on top of one another. 100 Dobson units is 1 millimeter thick. That's about the thickness of a dime. So the plot shows that ozone was declining in the 50s and 60s slowly, but then it precipitously fell in the late 70s to 1984. That's the last point on the right. These observations were October averages. The uncertainty on them is quite small. So we knew something was happening over Antarctica, but we didn't know what was happening. Satellites were also making observations in the 70s and 80s. The BUV satellite shown, or BUV instrument on the Nimbus 4 satellite shown in purple, and in red is the Nimbus 7 total ozone mapping spectrometer data. Now, the first image of the ozone hole is there on the right. This was made by P.K. Bhartia. Down there on the bottom right is P.K., who's at NASA Goddard. Very low ozone over Antarctica. In fact, continental in scale. It's a false color image, and the reds and yellows there show where ozone is quite low. It took an entire room of computers to create this particular image. So we knew that it was happening over Antarctica. We knew it was continental in scale. And in fact, there were previous balloon measurements that showed that most of the ozone loss, the change in ozone, was occurring between about 12 and 25 kilometers. Now, these results were actually shown in the 3-volume set. It was an international assessment, Atmospheric Ozone 1985. And that document became the scientific basis for the 1987 Montreal Protocol on substances that deplete the ozone layer. So the Montreal Protocol controls the production and consumption of ozone-depleting substances like chlorofluorocarbons. And I'll come back to that in a minute. Now the first theory of the ozone hole was proposed by Susan Solomon, Rolando Garcia, Sherry Rowland, and Don Wubbles. In this theory, they showed that in fact what was proposed by Joe Farman and his colleagues couldn't be correct because of course you needed oxygen atoms in this 12 to 25 kilometer layer above Antarctica, and that's hard to create those there at that time of the year, which is in early spring. They hypothesized that polar stratospheric clouds were present. They form at very cold temperatures, and that HCl and chlorine nitrate, these are the reservoir species of chlorine, they could react on the surfaces of PSCs to form nitric acid and chlorine gas. So heterogeneous chemistry with chlorine species was releasing chlorine that could then photolyze and cause ozone depletion. So in the 60s, 70s, and 80s, these chlorine species were going up quite rapidly. This is a plot that shows the amount of chlorine above Antarctica from the various species. CFC12, methyl chloride, methyl bromide, CFC11, and carbon tetrachloride. Also on there is methylchloroform in orange. So all of these gases, which are mainly human produced, methyl chloride and methyl bromide are natural, but the human-produced species were going up quite quickly. Methyl bromide is also used as a fumigant, so it does have a human-produced source. So these were going up. So the hypothesis was CFCs, chlorine is going up in the stratosphere, and it's being released, and it's causing ozone depletion. Now, a limitation on this theory is nobody knew what was the catalytic cycle that might be causing this. In 1986, Luisa Molina and Mario Molina proposed a particular catalytic mechanism that didn't include oxygen atoms. All you needed was a chlorine atom catalyst and ozone. So you go from the left side, start off with 2 ozones and 2 chlorine atoms. And on the right side, you have 3 oxygen molecules and again, 2 chlorine atoms. So these chlorine atoms could catalyze ozone depletion. And in fact, the rates at which it happens could be about 1% per day. So it's very, very rapid. Now, this was good. This has been shown in the lab, but we needed observations over Antarctica. In 1987, the NASA Airborne Antarctic Ozone Experiment was launched. This was a joint collaboration of NASA, NOAA, the Chemical Manufacturers Association, and National Science Foundation to take the NASA U-2, which is known at NASA as the ER-2, but it's a U-2, it's a converted civilian version of the U-2 spy plane, to instrument it, take it down, and fly it straight into the ozone hole. Now, at the time, there were 3 theories. The first theory was a dynamical theory, that you're moving low ozone into this 12 to 25 kilometer region. So they instrumented the plane to measure nitrous oxide, which could then be used to determine if that was true. The plane also included nitrogen oxide measurements, NO and NOY, and if the sun, the solar variations were causing enhanced NOx, then you'd be able to show that it was due to NOx. And then there's the chlorine theory that we've already discussed. Now, the reason I discussed the chlorine theory is because this is the one that turned out to be true. Of the 3 hypotheses on the cause of the ozone hole, it's the one on the bottom left there that proved to be right. And the reason it was right was because we measured CLO in ozone on the plane. Here are the ozone and chlorine monoxide measurements. Typically, we'd expect if it was just homogeneous gas phase chemistry, we'd expect to see very, very low CLO levels. Those are in black. Again, you can see that it's marked in latitude, so flying down over Antarctica from left to right. So over Antarctica, you're seeing up to about 0.75 ppb of chlorine monoxide. That's a lot of chlorine monoxide. Ozone there at about 0.8 ppm, ozone in red. So there's 3 things about this. First of all, the high levels of CLO demonstrated that chlorine was being converted into the reactive forms, as been hypothesized. The CLO-ozone anti-correlation showed that ozone was being destroyed. So if you look at the plot on the right, you can see where chlorine monoxide is high, ozone was going down. And it's actually anti-correlated. Where you have very low CLO, you have relatively high ozone. And the third thing is, you compare the 2 diagrams, you can see that ozone had dropped over Antarctica. So this is what is known as the smoking gun plot. The chlorine monoxide measurements come from Jim Anderson's instrument from Harvard University, measuring the CLO. So we knew that the cause of the ozone hole was the chlorine from human-produced compounds. Let me go into the details of how ozone depletion occurs over Antarctica. I'm going to show you a temperature graph to illustrate that. The temperature, when the sun sets over Antarctica, the temperature begins to fall off. You no longer have visible and UV radiation to warm the stratosphere. So it cools off quite quickly at 20 kilometers over the Antarctic. And you can see it gets down by mid-May, it's down below 110 degrees below 0 Fahrenheit or 195 Kelvin. Polar stratospheric clouds begin to form in these extremely cold temperatures. And in particular, nitric acid trihydrates form at about 195 Kelvin. If you get down to mid-June, the temperatures are cold enough to form water ice, very large water ice particles that can then settle out of the Antarctic stratosphere. Because of the PSCs, as we've already discussed, you begin to free the HCl and chlorine nitrate, the reservoir species, react on the surfaces of PSCs to form chlorine gas and nitric acid. So now we have the elements of ozone depletion present. So the sun begins to rise over Antarctica in the August-September period, and now you have the energy necessary to drive the catalytic ozone depletion cycles. So ozone is going down very fast in the August and September period. And it's August right now, August 2020, and in fact we can see from observations from satellites that ozone is in fact going down pretty fast right now over Antarctica, as we see every year. When you get into early October, the temperatures have warmed up enough, polar stratospheric clouds stop formation, and so the ozone depletion begins to shut down. So that's why we always see the lowest levels of ozone during October, which is what Joe Farman observed in his Halley Station observations. And the season finally ends. Temperatures get warm, the polar vortex over Antarctica breaks up, and low ozone gets mixed across the southern hemisphere. So the elements of ozone depletion are cold temperatures to form PSCs. The high chlorine over Antarctica reacts on the surfaces of the PSCs. You get the heterogeneous reactions, and that leads to large catalytic ozone depletion. So back to chlorine. This was what I originally showed you. In 1987, chlorine amounts were going up quite quickly over Antarctica, and the Montreal Protocol was negotiated. So this controlled the production and consumption of ozone depleting substances. So people didn't stop using them immediately. It took a little time. By the year 2000, the Montreal Protocol controls had been strengthened. Countries were ceasing production of these human-produced compounds, and the ozone-depleting substances began to decline. Mainly that orange stuff, methylchloroform, was declining quite quickly, has a very short lifetime. The other gases, like CFC12 has a lifetime of about a little over 100 years. CFC11 has a lifetime of 52 years. So ozone depleting substance levels are declining slowly over Antarctica. Back to the Halley Station data, you can see that in fact we can fit our chlorine levels over Antarctica to the Halley Station data. It fits pretty well. This is up to 1984. And if we add in the additional years going out to the present, 2019, there's no 2020 point yet for October, you can see that there's a hint that things are getting better. In the mid-1990s, there was an impact from Mount Pinatubo and Mount El Chichon. So volcanic aerosols can have an impact on the ozone hole, which led to these very low values you see in the mid-1990s. Of course, the satellites have also been making observations. Here you can see the long time series of satellites. In 1979, there was a low of ozone over the Antarctic, as we expect. By 1999, though, it had been severely depleted, so that we had very, very low ozone over Antarctica. In 2019, it appears that things are getting better, but there's a little bit of a hiccup there. Here are the October averages from 1970 to 2019. I've just picked out 8 for illustrative purposes. You can see in 1970, 1979 that ozone was relatively high over Antarctica, still a low there, but relatively high compared to the following years. You can see in 2000, quite deep, very low ozone levels over Antarctica. Again, the white line I've drawn around the 220 Dobson unit level. And we use that to calculate the area of the ozone hole. So the ozone hole was large and extensive over most years. Now, if you compare 2018 and 2019, you can see that 2019 is actually quite a bit smaller as an ozone hole. So let's take a look at trends of things going on over Antarctica. The top right plot is September temperatures, average temperatures, over the polar cap at 50 millibars, which is about 20 kilometers altitude. The middle figure is the September total ozone, averaged again over the polar cap. And the bottom right plot is we take the lowest value we see every day in September over Antarctica, and we just average them together, all these low values, and we come up with an annual value for low ozone over Antarctica during September. The note, you can see that there are certain years that are quite a bit warmer than others. So for example, 1988, 2002, and 2019 are all quite warm in comparison to the average. Now, because it's warmer, you shut down polar stratospheric clouds and you cut off ozone depletion. So ozone levels tend to be higher in these very warm years. So we understand that quite well. The magenta line here that you see in the bottom two plots is our chlorine EESC fit to ozone. You can see it fits fairly well. And the blue lines are the trends of temperature, total ozone, and minimum ozone from the 1999 to 2019. If we look at the temperature plot, the temperature trend is not significant. It's going up slightly, but that is not what we consider, that is not a statistically significant trend. The polar cap total ozone is a statistically significant trend at the 95% confidence level. So it looks like ozone is going up. And if we look at the September minimum total ozone, you can see that it is statistically significant at the 99% confidence level and following that magenta line really well. So we're seeing some great hints that ozone is improving over Antarctica. And if you look at model simulations, it's pretty clear it's due to the decline of chlorine over Antarctica. So the next question is, where are we going into the future? So back to my chlorine plot. This is a chlorine plot that extends out to 2100. So we take the levels of banks and levels, the things we know about production, and we can project forward on what's going to happen to all of our man-made gases because of the Montreal Protocol. And in this you can see that CFC12 slowly declines. Methyl chloride and methyl bromide, our natural compounds, are about the same. CFC11 also declines. Carbon tetrachloride declines. So you can see a nice general decline. Now, the white line shows where we get back to 1980 levels. Sometime between 2065 and 2070, there's a bit of uncertainty in that. So we can say that it's in the 2060s, 2070s that we ought to be back to 1980 chlorine levels over Antarctica. Now we can take these observations or these observations prior to 2020 and projections beyond 2020, we can put them into a model and see what happens to ozone in that model. Here's the model simulation along with a couple of images of data. The top left image is from BUV. I've shown some BUV data. The left middle panel is from the OMI instrument aboard NASA's OR satellite. And then the two images on the right are from the model. And the model projection is shown. There's the October averages for the model, and I put a nice red smooth line through there. And you can see that ozone got really bad around the year 2000 when chlorine peaked, and it gently goes back to where it was again in the 2060s, 2070s. That's really good news. So finally, a summary. The ozone hole results from a combination of increased chlorine and bromine, and they're from human-produced compounds. Because of the Montreal Protocol, the ozone hole appears to be on the mend. And finally, in 2019, we had a hiccup. It was a small ozone hole, but that was because of the meteorology. So don't expect this to happen in 2020. Thank you for your attention.